scientists trained 3 X-ray telescopes to observe this part of the sky for years after the event. And what they found was a strong and regular pulse of X-rays, brightening and dimming every 131 seconds. And it shows up in the data from all 3 telescopes. They observed periodically over 450 days, but the pulse maintained this rhythm and didn't get weaker. In fact, as time went on, the relative strength of the pulse got stronger, modulating the X-ray signal by around 40%. And what was causing these periodic flashes of X-rays? And what could it tell us about the black hole? Well, let's back up, because black holes are some of the simplest objects in the universe. By that, I just mean that they are characterized by only 2 attributes, mass and spin. Okay, there's also charge, but since black holes should essentially be neutral, mass and spin are the 2 that count. Mass is relatively easy to determine. Far away from a black hole, you can even use Newtonian physics. By measuring the gravitational effects of the black hole on other bodies, you can estimate the mass of the black hole. This has been done, and black holes have been found with masses ranging from just a few times our sun, stellar mass black holes, up to billions of solar masses, supermassive black holes. It's generally accepted that there is a supermassive black hole at the centers of most galaxies, including our own. But what about spin? Since black holes form from collapsing stars and all known stars rotate, all black holes should also be rotating. I mean, what are the chances that a bunch of matter just collapses into a point perfectly with no rotation? It's just not going to happen. And then additional matter falling into the black hole contributes its angular momentum. So like a figure skater pulling their arms into a point object, you can imagine black holes get spinning pretty fast. But spin is harder to measure because, unlike mass, it only affects objects relatively close to the black hole. But there is a way to do it. Actually, 3 ways. To understand all of them, you have to understand ISCO. In Newtonian physics, around a compact mass, you can place an object in a circular orbit at any radius, and it will be stable. It doesn't matter how close you get. This is not the case according to general relativity. Here, there is an innermost stable circular orbit, with a radius known as r ISCO. Closer than this, and no orbits are stable, they all fall into the black hole. So when you're looking at a black hole that is feeding, the innermost edge of the accretion disk is at r ISCO. What's useful for our purposes is that r ISCO depends on the spin of the black hole. The faster it's spinning, the smaller r ISCO becomes.